So we're going to talk a little bit about the comparison test for determining the convergence of series, and it makes very good intuitive sense. And I've written it up here on the board with a couple examples. If you want to be filling out a sheet while we're working through this, this is the sheet that you would be looking at here. So you can see it says comparison test with a couple of examples here, and there's some thinking questions for you to think about, which I won't talk about, but I'll allow you to think about those. So basically, it's this idea that suppose that we have a sequence that is less than another sequence for all values past a certain point. So we don't care so much what happens at the very beginning because, you know, those are just finite terms that we don't care about so long as, you know, this isn't some insane thing with asymptotes. And so as long as this is smaller than this after a certain point, then if B sub n converges the series of B sub n, then the series of A sub n will also converge, right? Basically we're saying that, well, this is going to be smaller than this, so if this one converges, then the one that's smaller than that should also converge. And I'm not sure what the word would be here, inversely or conversely, one of those. If the smaller one diverges, then the bigger one will diverge as well. So it's very similar to some of the comparison that we did with improper integrals. Oh, and this little symbol here means for all. Sorry, I forgot to mention that. For all n past a certain n value. Okay, so basically this allows us to deal with some things that are not, you know, beautiful p-series or beautiful geometric series, or can't be integrated well, you know, but maybe their sequences still approach 0. So you don't want to use direct comparison unless you need to, obviously. Something like a geometric series, you have a different test to use. Something like a p-series, you have a different test to use. But this can be useful in certain cases. So let's check out this first example right here. So it's good to always think intuitively about what you think is going to happen. And usually, and we're going to look at this test in a bit, you want to think about what happens as n gets large. So when I look at this and I think about what happens when n gets large, this 1 and this -1 just don't really matter, right? They're tiny little things compared to 2 to the n over n times 2 to the n. And then I'm thinking, well, the 2 to the n's basically behave the same, so I think this is essentially going to behave like 1 over n. So I'm going to say that it's like 1 over n. And so that means that I think it's going to diverge because I know that 1 over n is a divergent p-series with n equaling 1. So that means that what I want to show is that this is bigger than 1 over n. Because if I can show that this is bigger than 1 over n, then I have what I want. Because I know that the series of 1 over n diverges. So if I can show this is bigger, I know it would also diverge. That's this second piece here. So I'm going to get to work. So I'm going to start with, let's say, 1 over n. Okay, so I'm going to start with what I know, 1 over n. Now I'm going to say that this is equal to 2 to the n over n times 2 to the n. And what I'm trying to do is start with something I know and build it up to look more like this. And hopefully I'm trying to make something that's bigger that looks exactly like this. Because if I can show that this thing is bigger than this, that will be good. So I'm sort of building it up piece by piece. Now these are equal, right? Because 2 to the n over 2 to the n is equal to 1. Now this is less than 2 to the n plus 1 over n times 2 to the n, right? That's very obviously true because I just added 1 to the numerator. So this is now bigger, and I'm getting closer to what I want here. This is less than 2 to the n plus 1 all all over n times 2 to the n minus n, right? If I subtract n from the denominator, this thing gets way bigger, and that is actually equal to the original sequence I had. So this is where series can get a little bit complicated because I'm using a lot of experience to carefully show you that this is bigger than this. But intuitively, when I look at this, I think it behaves kind of like 1 over n. When I add to the numerator, things get bigger. When I subtract from the denominator, things get bigger. So in a sense, I'm making this bigger, and I'm just starting with what I know and then building it up to show that what I want is true, that this sequence is bigger than this sequence. Then I can make a conclusion and say, thus, by direct comparison with the divergent p-series, this series diverges. Okay, so, oh, I'm glad that that bottom line is still being shown there. So I'm basically just trying to prove, and all the work comes in proving that that sequence is bigger than another sequence. Okay, so now let's look at example 2 right here. Doesn't look like something that is a direct, it's not exactly a p-series, it's not geometric. But intuitively, I'm going to think n squared over n to the 4th, that looks a lot like 1 over n squared. So I think that it is going to converge. That's my guess, because it looks like it's going to behave a lot like 1 over n squared. So then what I want to do is hopefully show that this thing is smaller than 1 over n squared. Well, I'm in luck because adding to, adding to the denominator is going to make this thing smaller, so I think this is going to be a good situation. So I want to show that it is smaller than this, because if it is smaller than this, then it will converge. That's the second thing right here. If one series converges, and the series of a smaller sequence will also converge, then it will converge. So let's start with what we know, which is 1 over n squared. And let's build up to this, hopefully getting smaller. So this is equal to n squared over n to the 4th. And if I add 1 to the denominator, I get something that is bigger. Now, I don't get something that's bigger, I get something that's smaller, which is good because I want it to be smaller. I'm afraid I may have moved off the screen, so I'm just going to move this back just a little bit. Start with 1 over n squared. That's equal to n squared over n to the 4th. That is greater than n squared over n to the 4th plus 1. Adding 1 to my denominator should make the fraction smaller. And that's all I need. All I need is for this to be smaller than something that I know converges. And I can say, thus, by direct comparison with the convergent p-series, this series converges. So that's direct comparison, and the whole idea is think about something that you think is very similar. Just move this over so you can see that. But that you think is very similar to your series, behaves similarly, and then show that it is smaller than something that converges or bigger than something diverges, and you'll be able to make an appropriate conclusion.